This video is over topic 46, sequential probabilities. So as with sequential counting, the probabilities get multiplied together. So this is when you have the probability of this happening and this happening and this happening step by step. Now, probabilities get multiplied together, but both the sample space and the outcome, the event space, you have to watch for. If these are dependent, then the previous step is going to affect potentially what's in the sample space and also potentially the outcomes within the event. If they're independent, then it's just straight up multiplication. So, number one, probability of flipping a coin twice and getting tails both times. Now, we did this previously with a sample space. The sample space for flipping a coin twice can be written as something like HH, HT, TH, TT, 4 outcomes. And flipping a tail twice is just the one of those. So one of the 4 outcomes, probability is 1/4. Now I can also calculate this as a sequence of steps. So I don't have to write out the sample space and figure out which elements, I don't have to count how many there are in the combined. I just have to look at each step. So flipping a coin 1 time, tails is 1 out of the 2. Flipping a coin 2nd time, tails is still 1 out of the 2. So for the combination of those, for the sequence, multiply 1/2 times 1/2 equals 1/4. Right, so next example, student ran out of time on a multiple choice quiz, has to guess on the last 2 answers. Each question has 4 options, with only 1 correct option. So probability the student gets both questions correct. So question 1, what's the probability? He's randomly choosing out of 4 options. 1 of them is correct. There's 1 correct out of 4 options. So the probability is 1/4. Second question, same deal, 1 correct out of 4 options, 1/4. So the combined, the probability of both of those things happening is 1/4 times 1/4, which comes out 0.0625, or rounding to 3 places, 0.063. Then the probability the student gets both questions incorrect. Well, for the first question, that would be 3 out of the 4 options are incorrect. So 3/4 probability. Same thing for the next question. Multiply those together. And that comes out 0.5625. 3 places is 0.563. Right. Then next up, this one ends up kind of tricky, but let's look through this. So a fair die is rolled 5 times. So we have first roll, second roll, third roll, fourth roll, fifth roll. What's the probability that 1 is rolled at least once? Now, if we try to calculate this directly, well, that could be the first is a 1, then the second, third, fourth, fifth could be anything. Or if the first isn't a 1, then if the second's a 1, then we're done. And then if neither the first or second is a 1, then if the third is 1, we're good. But if none of the first 3 is a 1, the fourth is a 1, all good. Or if none of the first 4 are 1, the fifth is a 1. We'd have to find all of those probabilities, add them together. And those would involve, various sequences. So you'd have like, so 1, probability of 1 is 1/6. Probability of not 1 is 5/6. So you'd have like 1/6 times 5/6 times 5/6 times 5/6. In fact, it would be 1/6 because then the others could be ones also. So 1/6 for the first to be a 1. Then if the first isn't a 1, that would be or. First isn't a 1, you'd have 5/6 for the first to not be a 1, 1/6 for the second to be a 1, and then whatever else happens doesn't matter. But then you'd have, okay, what if the first and second are both not 1? 5/6 for both those, and then 1/6 for the third to be a 1, the rest don't matter. And then so on. You'd have two more things. You'd have to multiply those and add them all together. So don't want to do that. Another way is to say, well, there could be 1, 1 in any of the roles. And you have to figure out how many ways are there for there to be 1, 1 mixed in there. That would be 5 ways. But if there are 2 1s, then you have to figure out how many ways are there to, how many ways are for the 2 1s to be positioned amongst the 5 roles. And that gets more complicated. And you have to add those. So don't want to mess with that either. So this is a case where it's easier to look at what is this not. So going back, we have our 5 roles. So if all of them are not 1, that's the only situation that doesn't. So probability 1 rolled at least once, or let's do it this way. If A is the event that at least 1 1 is rolled, then not A would be no ones in any of the 5 rolls. Now that we can calculate. Probably the first is not 1, 5, 6. Probably the second is not 1, 5, 6, and so on. Okay, so we can find probability of not A is this calculation, or you could do 5/6 to the 5th power. Okay, so you do that. That's 0 point whatever it is. Then probability of A is 1 minus probability of not A. That's 1 minus the 0.4018, whatever. Uh, 0.5981. Okay, so you'll have something similar to this in the homework activity 11. There's also at least potentially a question in the homework in Alex that might have something like this as well. So recognizing when it's like at least once that's everything other than not at all is the big key there. All right, number 4, a coin is flipped and a 20-sided die is rolled. We want the probability of getting heads on the coin and a multiple of 3 on the die. So heads on the coin, that's 1 out of 2. Multiple of 3 on the die, we're looking at a 20-sided die, so multiple of 3 would be 3, 6, 9, 12, 15, 18 are the multiples of 3 between 1 and 20, so 6 of those, 6 out of the 20. And probably to both of those things happening, you multiply. So generally you'll see and, if you have an and, it may be a multiplication versus addition would be only if there's an or. So heads of the coin and multiple of 3. 1/2 times 6/20 is 6/40 or 3/20. Then number 5, we have the adults in a large church congregation are made up of 170 married men, 20 unmarried men, 180 married women, and 40 unmarried women. If a random man and a random woman are chosen, what's the probability that both are unmarried? So really this is saying what's the probability of choosing an unmarried man out of the men and choosing an unmarried woman out of the women. So this is not choosing two people out of the whole congregation. It's choosing one person out of the men, one person out of the women. So this is going to be the number of unmarried men out of the number of men altogether. This is going to be the number of unmarried women out of the total number of women. Those two will then be multiplied together. So the key is like this is multiplication, not addition. We're not going to take the number of men plus the number of women. We're not going to take the number of unmarried men plus the number of unmarried women. We're going to multiply. So there is, let's see, 20 unmarried men, 170 plus 20 men altogether. So that's 20 over 190. There are 40 unmarried women, 180 plus 40 women total. So that's 40 out of 220. Those two get multiplied together for the final result. Do 20 divided by 190 times 40 divided by 220 is 0.019. Let's see. Okay. Then an appliance store gets a shipment of 25 plasma TVs. 3 of them are defective. 2 TVs are chosen at random. Find the probability that both are defective. First TV is not replaced after. So we're going to have the first choice. We're taking out of all 25 TVs, 3 are defective. So choose 3 out of the 25 are defective. So the probability, so this is looking for probability. First is defective, and second is defective. And what this is going to be is probability first defective times probability first defective, or sorry, second, probably the second is defective, given that the first was defective. So probably first is defective 3 out of 25. Once we assume that the first was defective, that's what the given that the first was defective, now there are 2 defective left out of 24 total left. So 3 out of 25 times 2 out of 24 comes out 6 out of 600, or 1 out of 100. Number 7, we are looking at 68 teams altogether. We have some of the team descriptions included, not all of them, but you're randomly assigned 2 teams. So there's going to be a first and a second. Probably both were from the Big 12. Again, probably the first was from the Big 12. There was 6 in the Big 12 out of the 68. Then the second given that, assuming already that the first was from the Big 12, then the second, there's now only 5 left from the Big 12 and 67 left to choose from. So 6 over 68 times 5 over 67. 0.007. Then probably the first was from the SEC. SEC is 7 out of the 68. And then the second choice, there's 67 to choose from. The Big 10, 8 from the Big 10. There's still all 8 because we're assuming the first was from the SEC, therefore it didn't affect the Big 10. So 7 out of 68 times 8 out of 67. 0.012. Number 8, we have a vase with marbles in it. And the marbles are 3 red marbles and 2 green marbles and 5 white marbles. For a total of 10 marbles. And we're going to pick a marble, note its color, put it back, repeat. So probably picking 2 green marbles, again, not picking 2 marbles at once to see if they're green, but picking one, put it back. So it's going to be, these are going to be independent because we're putting it back. So probably picking a green marble twice is going to be first time 2 out of the 10 are green. Second time we put it back, so still 2 out of the 10 are green. So that's 4 100ths or 1/25th. Picking a green marble and then a white marble. Green is 2 out of the 10. White is 5 out of the 10. Multiply those together. It's 10 out of 100 or 1/10. Then picking a white marble, 5 out of the 10. Then a red marble, 3 out of the 10. Then a green marble, 2 out of the 10. Now, the order matters. So this is white, then red, then green. If I said the probability of picking one of each color, you'd have to do white, then red, then green, white, then green, then red, then green, then white, red, then like there'd be 6 different possible ways to get one of each color. You'd have to calculate all of them and add them together. Or there's other, so if you get into probability beyond this course, we're sticking to the kind of this keeping things simple and imposing this order rather than saying the probability of getting one of each color would be a much more complicated calculation. This is going to be 30 out of 1,000 or 3 100ths. All right, as part of a card trick, a card is drawn from a deck and replaced, then a second card is drawn. Now, with the card trick, there's probably shenanigans going on, but what makes a card trick be a trick is that, assuming if there's not a trick, this is what you would expect. So we're looking at what would be the normal probabilities with no trickery involved. So drawing a card and replaced means we're looking at independent. So we're assuming each draw is out, any card equally likely to be drawn out of the 52. Probability of getting a queen on the first draw, there's 4 queens out of 52 total. Second draw, there's still 52 total because that queen got put back. 4 aces out of the 52 total. So 4 out of 52 times 4 out of 52 is 0.006. Number 10, cards are being drawn one at a time and not replaced. So now the first draw is out of 52. The second draw is out of 51. The probability of getting 2 queens, the first one, there's 4 queens total. The second one, we have to say if the first one was, so we're assuming that the first one was a queen, then there's only 3 left, queens left for the second draw. So 4 out of 52 times 3 out of 51. About 0.005. Then number 11, this is going to be 3 cards drawn and not replaced. So that means the out of is going from 52, and then there's only 51 left, and then there's only 50 left. And if we want 3 jacks, there's 4 the first draw. Once that first one is a jack, there's only 3 jacks left for the second. And if the first 2 are jacks, there's only 2 jacks left for the third. So 4, 2 times 3 out of 51 times 2 out of 50. And watch this, it's not 3.6. So probability cannot be greater than 1. So I want to look at the right end of the number, see that e minus 4. So this is 3.6199, whatever, times 10 to the negative 4, which is going to be 0.00036. Getting an ace, a king, and a queen in that order. Again, it's going to be out of 52, then out of 51, then out of 50. Ace the first time, 4 possibilities. If the first is an ace, there's still 4 kings in the second draw. And if the first 2 are an ace and a king, there's still 4 queens to choose from. So 4 out of 52, 4 out of 51, 4 out of 50. And that still has the e minus 4 at the end of it. Now it's 4, 8, 2, 6. And so that's going to be 0.00048. And backing up a little bit, I hit 6 instead of 3 on that previous one. So 4 out of 52 times 3 out of 51 times 2 out of 50. It's 1.8. $1.8099. So 0.00018 on that. All right, then the probability of getting a club, a spade, and a heart. Again, first draw is out of 52, second is out of 51, third is out of 50. A club on the first draw, there's 13 clubs out of the 52. Second draw, the first one drawn was a club, so all 13 spades are still there. Third draw, there was a club and a spade, all 13 hearts are still there. So 13 out of 52. Times 13 out of 51 times 13 out of 50. 0.01657.